Assalamu alaikum dear students, and welcome to Seismology. In our previous lecture we talked about the elastic rebound theory in detail, and also we discussed the faults. So now moving on to the geometric notation. So now you understand from the previous lecture the seismic moment, and if you knew the geometry of fault and you knew how much it slipped, you could compute the seismic moment, and if you also knew the shear strength of the rock, you could compute it. So now we are going to do this little figure here is we are going to learn a little bit about how we describe the geometry of faults and the geometry of earthquakes. Okay, so let's say that we have ground surface here represented by this oval, and we have a happy student walking along the ground and on the ground surface. Now let's say somewhere down beneath the earth surface that some depth rupture occurs on a fault and an earthquake occurs. So if with that location where the rupture initiated, the initial asperity broke the fault, we call that the focus, or sometimes we call it the hypocenter of the earthquake. It's the very location in three-dimensional space beneath the ground surface where the earthquake began. Now, if we just draw a straight line straight up from the focus to the ground surface, that the length of the line is what we call the focal depth, and then that location on the ground surface directly above the focus or the hypocenter, that's what we call the epicenter. Some people confuse the epicenter with the focus, thinking that the epicenter is down in the ground. It's not, it's just the projection of the focus onto the ground surface. Now from the epicenter, if we just draw the shortest linear distance from the epicenter to our happy students is probably now unhappy because of the earthquake. So that shortest linear distance is what we call the epicentral distance, and then if we take the shortest linear distance from the focus to our student, that's what we call the hypocentral distance, or sometimes we call it the focal distance. So looking at fault notation, let's imagine now we have this fault. So we have again this fault plane which represents the fault diving down into the earth. Think of this again as our three-dimensional drawing that we had before. Okay, yeah, something like this. Okay, anyway, couple things first. The angle that the fault plane dives, that angle from the horizontal, so it's the angle from the horizontal that fault dips down, it goes down into the earth. That's what we call the dip. Okay, so now the strike is the orientation of the intersection of the two blocks of the earth. So in other words, you can see in this instance, this first block intersect the second block, and if we just draw a line along that intersection, the orientation of the line is usually in terms of an azimuth. That's we call the strike. So if I go back to my little drawing here, and I have used that black line, the intersection of that block on the right, that's going down on the block on the left, and staying that right here is the stripe, and it's going to have some geographic orientation. It could be pointing to the north, it could be pointing to the northeast, to the east, or whatever. It could be slightly curved, rarely are they totally linear, but that the intersection is what we tend to see is a fault on the ground surface, and its orientation is azimuth orientation is what we call the stripe. So it's the stripe of the fault. Okay. All right. So if the dip is the downward dive of the fault, then the angle of the dip is what we call the dip angle. So if I have a fault that I call a strike slip fault, that means that the fault is going to move in the direction on the strike. So if I go back to my little figure here, strike slip fault means, and instead of moving down my block, it's going to move parallel to the direction of my strike. So I'm going to have translation instead of up and down motion. Okay, so that what would be called a strike slip fault. So now if I get up and down sliding on my fault plane, meaning that the block is now sliding in the direction of the dip, then I have what's called a dip slip fault. So this happens when I have compression going on between the rocks, and this thing slides up relative to the block on the left, or if I have extension going on, and it's extending this block on the right side down the dip face relative to the block on the left. So but either way, if it slides up or down, we call it a dip slip. So you have strike slip, meaning translation movement in the direction of the strike, or dip slip meaning up and down movement on the fault plane in the direction of the dip plane. So let's learn a little bit about the different types of faults, okay, crustal faults. Okay, so one of the most common types of crustal fault is the strike slip fault. We just like what we just talked about. So this is the fault where you have the horizontal translation in the direction of the default strike. So you tend to see this with the transform regime. There's two types of fault. You have a right lateral strike slip and a left lateral strike slip. The way to remember this is, imagine that I have one person standing on one side of the fault and another person standing right across on the other side of the fault. So imagine that those two persons are friends, and they reach across the fault and they shake each other right hand. If an earthquake occurs, while they are shaking each other's right hand, and the person whose hand they are shaking moves to their right, in other words, they shift to their right, that means it's a right lateral strike slip fault. So if the person whose right hand they are shaking across the fault moves to their left, then you have a left lateral strike slip fault. So this particular fault that we are showing right here, where you see these arrows, they are indicated. Would this be a right lateral or a left lateral strike slip fault? That's right. So it would be a left lateral. In other words, if these people are shaking hands across the fault, the person across the fault would be moving to their left. So that means it's a left lateral fault. Typically, these dip angles are around 90 degrees. So you have like a vertical fault basically, and we usually see these types of fault associated with strike slip fault. Okay, so now some of you might be wondering that what in the world am I doing showing a beach ball on this figure? What does that have to do with anything? So okay, so we try to remember the right name for these. I believe they are called stereo net projections. That's the correct term for them. But I never call them that, and the people I associate with never call that. We just call them the beach balls. And what they are two-dimensional representations of the movement along fault. So to understand stereo net projection, imagine an eyeball. As in an eyeball, here I can draw it, and that eyeball is positioned directly over the top of the fault, looking straight down. Okay, so you imagine then that the eyeball was looking at a circle of the ground directly over the fault. So that eyeball would just see a straight line representing the strike of the fault. That was just straight line here represents the strike of the fault. Now there's going to be a portion of that fault where the ground move one way, and a portion where the ground move another way. So if you imagine the ground moving, and imagine if this block here on the left move as the right lateral motion, and let's say that I had a block of soil right here next to this big block, and let's say that block did not want to move at all, but this joint block just thrust and shoves it right into my block right there. That block of soil is going to get pushed, and it's going to get pushed because it feels compression. So now if I have another block of soil right here on this other side attached to this block, and this block moves this way, so you can see that my little block right here I was going to get pulled with this block. Okay, so in other words, there are going to be tension. So with that little block there, wherever there is compression, there's going to equal black on my stereo net. Wherever there is tension, that's going to equal white on my beach ball. So check out that I have black right here, meaning that in this quadrant I have got compression, because it's that soil is being thrust in left lateral way, and then this quadrant here on here I'm kind of outlining. I want you to outline this. It's going to stay white because it's in tension from the movement eyes. Opposite over here, this quadrant where my left lateral motion gets thrust to the right, it's going to cause compression in this portion of my little circle, but tension and the other portion, so compression, it's not so messy compression, and then the white is tension. So this would be indicated, then this beach ball would be indicated of left lateral strike slip fault. So if it was a right lateral strike slip fault, then the colors on the beach ball would be opposite. Well, let's look at a different one. There's another type of fault called a normal fault. They are associated with tensile regimes. A normal fault does not experience strike slip. A normal fault experience dip slip, but it's down dip slip, meaning it occurs typically in extension regimes. And in extension regimes, as the earth is spreading out, the ground has to spread too. So often what happens, this is the case. So let's say that we have, this is my mountain range with a valley. Let me show you that. Mountain range with a valley in the middle. Okay, so if we have mountain over here and here, and then we have a valley right here in the middle. Okay, so if this is an extension regime, that means that something is pulling this whole ground, these mountains apart. So if tension and extension pulls these mountain apart, that means this valley here in the middle is going to slide down. It's the only way that the extension can happen. It's the only way that the earth can stretch out. So this is particularly geography here, or the geometry is what we call is graben. It's very common in extension regime. So interestingly enough, we call it a normal fault, but the reality is a normal fault is not so normal. Compression and transition are much common geographic or geologically speaking than extension is. So it's really the least common of fault. The fault, there's a couple places in the world where there's a lot of extensional faults. The Intermountain West in the US is one of them. The Rift Valley or the Rift Zone in the East Africa, or in another entire country of Italy, basically is extension fault in regime. And there is other places as well, like the typical dip angle of these faults. The dip angle is between 50 to 75 degrees from the horizontal. And again, we usually see these types of fault associated with gravens and valleys. So a good example of one of these faults would be the Westwatch fault, which is located to the east of Brigham Young University. So if we do our stereo net projections here, the eyeball looking down on the fault. So let's draw my circle over here, and what we see, this little section right here is one of the fault scarp. That is the middle section right here of my stereo net projection. You can see that somewhere in here I am going to able to see the stripe. So this would be the stripe of the fault. Okay, and again remember, this block is sliding down. So if I had a block of soil that could measure pressure down here, and this block slide into it, I would register compression. So it's going to be black. And if this block, if I had a little sensor of soil up here, and this block on the left side up, and it would be registered pressure and our compression, and it would show as black. So that's why I have black up here and black down here, but white in the middle, meaning tension. So you got to think of it, everything it's sliding down but up, but everything sliding away. So it's just indicative of extension. So yeah, these stereo net projections, they look like eyeballs with the white centers. That they indicate of a normal fault. Reverse fault, these are also dip slip faults, but these are different than normal faults, because instead of extension, now we are dealing with compression. So instead of two blocks sliding away from each other, they are sliding toward, they are pushing against one another. And the fault movement slides up the dip plane, not down the dip plane. So these are very common types of crustal faults. They are also very scary because when you are dealing with compression and rock, you are dealing with huge forces and massive energy release. So reverse faults can be very large earthquake, and the typical dip angle of these types of faults, they can vary. They can be really shallow, like 10 degrees. If you have a really shallow reverse fault, it has a special name. We call it a thrust fault. So a thrust fault is just a very shallow reverse fault, but that could also go up to about 55 degrees a dip angle, and so we just call that a reverse fault. So again, with really low dip angles, usually less than about 40 degrees, we are going to classify them as a thrust faults. Remember that reverse faults are typically the most powerful of all the crustal faults. They produce the largest earthquakes. Some examples of some reverse fault or thrust fault include Seattle fault, which runs right through the middle of downtown Seattle, or maybe the Himalayan frontal thrust fault over in the Himalayas. So here is our stereo net projection. It's look like it's the exact opposite. The inside of our eyeball is compression, the outside is tension, but the corners of the eyeball still represent that this angle of the striking of the fault. So if you ever see a projection like this on a seismic map, then you know that the fault is a reverse fault. Okay, so now there is no rule that says that the earthquakes have to happen in the fault, normal fault or the fault. I'm sorry, that the earthquakes have to happen in the strike slip or the dip slip orientation. It's the possible that they can be upshore or have rupture with a strike component and a dip component. So if an earthquake rupture down the dip plane but also along a strike plane, then it is what we call an oblique fault. Okay, and most fault have some level of obliquity to them. To theirs, it's very rare to have fault that is purely strike slip or purely dip slip. The stereo net projections, they look like a mixture of either like a strike slip projection with either a reverse or a normal fault projections. So that was all about the different fault types. So you guys just go through the lecture, and if you guys have any queries, any questions, you can reach me through this email. Thank you for your time.